Right, so we have met hypothesis testing twice already in the syllabus. We met hypothesis testing with the binomial. And with the binomial, we said, right, okay, here we are doing something, some activity, a number of times. And every time we do it, there's a particular probability of success. So it might be, 10 games of tennis against Pat and James or whatever. And we used hypothesis testing to say, okay, we currently think that that's the probability, but actually, Mr. Gobber and I played James at tennis 10 times the other day, and we won 7 games. Does that mean that the probability is still that, and it's just, an unlikely result because unlikely things happen? Or maybe has the probability changed? So the alternative hypothesis is one of 3 things, isn't it? It's either that, so I need an example. Let's use my example from yesterday where it was 10 and the chance of me and Mr. Gobler winning was 0.1. So the probability that is 0.1, that's our null hypothesis. So we're either going to say, right, we think the probability is greater, or the probability is less. That's called a one-tailed test, isn't it? And then sometimes we say, actually, we just think the probability's changed, but we're not really sure which way, and that's a two-tailed test. So that was hypothesis testing for the binomial. We then met hypothesis testing with correlation, where we had a set of data, and we had this value R, which was the correlation coefficient. And we also had this idea that that was the correlation coefficient for that sample, and we then had rho, which was the population correlation coefficient. And when we do correlation, we think, okay, we've done, historically, we think that the correlation between this and this in the population is equal to something or other. Remember, that's always a number between -1 and 1. But maybe we think that, I apologise. With correlation, we always say, our null hypothesis is that there's no correlation, don't we? No correlation. And then we say, okay, let's test to see if there's a positive correlation. That's a one-tailed test, using a test result from a particular sample. Let's test for a negative correlation. Those are both one-tailed tests. Or maybe we're saying we think there might be a correlation, but we don't know which way. That would be a two-tailed test. And so today we're going to add, and I don't think that will appear on the camera, so I'll put it here, hypothesis testing with the normal to that set. I'm going to leave that empty for the moment. Have I got? So I want you to imagine that I somehow calculate the heights of everyone in the school, okay? And we discover that, like most continuous data, the heights of people at the school are normally distributed, and let's say that the average height is 150 and the standard deviation is 12 centimetres, okay? It's a very bad symmetrical. Try again. So you could say, well, hypothesis testing is where you say, right, at the moment I think the mean is 150, so I'll take someone's height and test it to see if it confirms or denies that the mean is 150. So I pick Pat, and Pat's height is here. So I say, well, that's really unlikely. I must have this wrong. The mean can't be 150 because I picked someone and their height is up here. Or maybe I pick a year 7 student who is somewhat diminutive and they're down there. Again, could I say, well, hang on a minute, so the mean can't be 150? Well, we can't do that, can we? We can't with single values make a judgment about everything. And that's not what we do here, because here when we test, we've tested with a set of 10, whatever it is. And here, when we're testing to see if we're right about the population product moment correlation coefficient, we're testing it with a set of data. So what we need to do when we use hypothesis testing with the normal distribution is we need to use a sample of data. But it's not quite as straightforward as that. Because if I take a sample of data, one sample of data, that's not really enough. So what you have to imagine is that we've, over time, taken lots of samples, okay? So you have to imagine for correlation, for hypothesis testing with normal distribution to work, you've got to imagine that over time we've taken a lot of samples. And let's say all of those samples are the same size. So let's say, and each time we take a sample, we work out the mean and the standard deviation. And we then look at the mean and standard deviation of those means. So we look at the results of each sample and we look at how they are distributed. So what we're doing is we're saying, okay, what's the distribution of the means of those samples? This next bit is hard to get your head around. So what I've got here is I'm saying that the heights of every student in the school are normally distributed with these parameters. But what we're doing now is we're saying, okay, what we're saying now is that we've got lots and lots of samples, and each of those samples has a mean, and we're looking at the distribution of those means. So I took a sample of students the other day, worked out the mean height, and then I took a sample yesterday, worked out the mean height. And the question is, that's going to be normally distributed, but how is the distribution of those means going to compare with the distribution of the actual heights? And the fact is that although the mean of the means of all of those samples should still be roughly 150, you're never going to get a sample of, say, 20 students from the school with a mean of this height, because any sample, if chosen well, will have a few tall people and a few short people. So actually, you're going to always end up with a value in the middle here. So when you look at the distribution of the means, you get a much narrower distribution. And when we are looking at a sample of heights and trying to decide whether they support or challenge a particular understanding of the mean of a set of data, we have to consider this distribution, not this distribution. And it can be shown that if you have a set of data that's distributed like this, and then you take lots of samples of that set of data, the distribution of the mean of those samples will have the same mean as the population, but its standard deviation will be divided by the number of values. Because the more values you have in your sample, and that N isn't the number of samples, it's the size of each sample. So if you have a large sample, then the average is very likely to be very close to 150. And if you take lots and lots of large samples, they're always going to have a similar result. So you're not going to get the same spread as you do with the actual heights when you look at the samples. And we need to do hypothesis testing here. Not here. Now, there's two things here really. There's struggling to get your head round why this graph is narrower than that graph. And there's just not being able to get your head around that and just remembering this is what we need to do. Now, I'm hoping that we are all at the moment in the latter category. We can all, by the time we've done a few examples, remember to do that. I struggle to get my head around it, okay? And you know, it's the second time I've taught this because this was new on the spec, and I can remember the first time around 4 years ago, shocking. No, 2 years ago, sorry, 2 years ago. Yeah, struggling to get my head around it. So it is tricky to get your head around, but I'm hoping some of you will be able to get there because some of you are much more capable than me. So let's look at some examples, and we're going to look at 2 examples from the book, and then I'll get you to try one yourself. We may even have time for a few more. So we are on. Oh, we are frozen. I think it's page 55, but I'm locked out. Sorry. Does page 55 look correct?
Tell you what, on top of page 56.
So this is hypothesis testing with the normal distribution. Does it? What? 56. And there should be 2 examples, one on each page. And that's where I'm headed. Sorry, I'm just being locked out. I left it before. Oh, sorry. I'll try one more time, and then I'll just go. Okay, yes, example 14 on page 56. Example 14 on page 56. So here we've got a set of normally distributed data. So the first thing I need to do is to write down what the parameters of that normal distribution are. So I'm looking for a mean and standard deviation. I'm going to use, what letter shall I use? They're using X, so I'm going to use X. And so X in this case is the amount of juice in a carton. And I have to hunt, the standard deviation is 3. So, and then the mean is 60. Now the trading inspector suspects that this company is up to no good. It's making over-ambitious claims. So along comes the inspector and he or she takes a sample. And that sample is 16 big. And it gives us a value. The mean of that sample is 59.1. We can't do hypothesis testing with this distribution. We instead have to firstly do the adjustment that says, right, because we're dealing with the mean of a sample, we have to compare it with the distribution of means of similar samples, which would give us that. I did write variance. Yeah, so the variance, the standard deviation squared, gets divided by the size of the sample. And that's a much skinnier distribution. And I'm going to work out the standard deviation, which is the square root of that. Because in this case, it's quite a nice value. 3 squared is 9 over 16. Square root of that is 3 over 4. So I am about to use hypothesis testing to see whether this result that they got, 59.1, is fishy, or whether it's just because sometimes you get more and sometimes you get less. So my null hypothesis in this case is that the mean is still 60. But my alternative hypothesis, well, is it a one-tail or a two-tail test? Let's read the question carefully. The trading inspector has received complaints that the company is overstating the mean. So the trading inspector is suspicious and thinks that actually the mean might be less than 60. So we've got a one-tailed problem here. We're being told to check at the 5% level of significance. Let me remind you what that means. That means the value here such that any value less than that has a probability of 5%. What that means is something that's so unlikely it's only going to happen 5 out of every 100 times. Because unlikely things do happen, but you get to the point where you're just saying that's just too unlikely. It must mean that actually that's not right. And of course 5%, we know that sometimes we test at a far stricter level. 1% is far, far stricter. That would be only if it's so unlikely it only happens 1 out of 100 times. So we've got two options. We can either work out the critical value for 5%. And we do that using the inverse normal function on our calculators, entering mean is 90, standard deviation is 3/4. Or we take the value we've been given, 59.1, and we work out the probability of 0 to that and see if it is bigger or smaller than 0.05. You've got the two options, and hopefully once you've taken one of those two options, you'll be able to make a statement about this. Go and see if you can investigate. The observed value they got for that one sample was 59.1. We all calculated that. So it's statistics, normal, not binomial, normal.
Do you do the inverse?
So if you're going to do it this way and use the inverse, you're going to say, right, left tail, area is 0.05, and it will tell you that value, and you've got to compare that value with 59.1. Or you can use the cumulative normal distribution with lower 0 up to 59.1 and see if you get more or less than 0.05. So the key thing though to remember is that we're entering this value, or the square root of that value, which in this case is 3/4, as our standard deviation, not 3, not 3. So when I look up the critical value, which isn't a probability, so I'm not going to go to 4 decimal places, I get 58.8. If instead I don't use the inverse, I use the normal cumulative distribution and go from 0 to 59.1, which was the value they got, I get an area of 0.1151, which is a probability, so I am going to round it to 4 decimal places. Whichever way you do it, 59.1 isn't unlikely enough for us to reject the null hypothesis. So we don't have enough evidence to reject the null hypothesis. There's not enough evidence to suggest that the mean is less than 60. And we always have to write that sentence both out of context, there's not enough evidence to reject the null hypothesis, and then in context. which means that we don't have enough evidence to support the complaint that the mean is less than 60 millimetres. The key thing is, because we are looking at a sample mean, we have to think about what the distribution of lots of means of lots of samples would be. It wouldn't look like this, it would look like this. So have a look at this second example, which you'll see on the next page. See if you can sort of fill in the framework, including the hypotheses. There's a slightly fiddly problem with the actual standard deviation here, but see if you can get to that point. So I'm hoping you can see what's going on here. We've got the original distribution, but because we're dealing with a sample of 50, the distribution of the means of lots of those samples would look like this, with a mean that's the same, but with a much narrower variance, which we square root to get the standard deviation. My null hypothesis is that the mean is unchanged. But at this time, the distribution of, it says here, to see if the mean diameter of the bolts has changed. Not if it's bigger, not if it's smaller. So that means that we're dealing with a two-tailed test. So we need to look at the top and the bottom. And this time we're being told to use a 1% hypothesis level, which means we need to split our probability in half. So rather than saying we're looking for 0.01 here and 0.01 there, when it's a two-tailed test, we half it. So we're actually testing to see for a 0.005 there and 0.005 there. And this question specifically asks for the critical region. So I'm going to use the inverse normal function, and left area 0.05, right area 0.05, although of course it is symmetrical. So actually you could say once I've got one, I can work out the other. It's slightly fiddly typing that in, because you can work that out and store it, but once you're in stats mode, you can't get it out. So the way I found I had to do it was I had to type in square root and then open some brackets, 0.015 squared divided by 50, close some brackets, just to make sure it's all under the square root sign. It may be that I'm being overcautious with the brackets, but I just wanted to be careful. You get the right number of zeros, because we were just doing 0.05, now it's 0.005. Unsurprisingly, it's symmetrical. But we haven't answered the question, because it says find the critical region. We found the critical value. So the critical region is that the mean of the sample has to be less than 0.575 or greater than 585 in order for us to worry. And that means in this case, we're worried. Alarm bells. 587, that's bigger than 585, so we do have sufficient evidence to suggest, to reject the null hypothesis and to suggest that the mean has changed. And note that we only say the mean has changed. I know it's obvious that the mean may be bigger, but because it's a two-cell test, we just say that the mean has changed. Page 59, 4 and 5. Here's what we're going to do. It was quite a good example, because I gave you all the Freddo before the question, before the lesson, and a psychologist here is testing to see if eating chocolate can improve your intelligence. If only. If only I'd be a genius. So to change it from
normal to a mean, you have to remember that you have to, was it in the book, that you have to divide it by the number.
Yes, you do. Yes, James.
So when it asks for the critical region, is it asking for the bit between those two numbers? Or the
Right, so it's a good question. No, it's the exclusion. So it's the bit that will make the alarm bells ring.
So it's the opposite of that.
That is correct. It's in this case, it's yes, it's going to be the two separate statements.
Okay.
Yeah, yeah. So yes, Pat. So the thing that sort of makes you think that you've got to divide by the size of the sample is that it mentions hypotheses. So as soon as you get into sort of the word hypothesis, you've got to think, right, I'm not comparing it with the original sample, with the original distribution, but with this sort of theoretical distribution of lots of means. Yes?
Is the x with the line on top the...
That is the distribution of means, because x bar is the mean of samples.
So what number is that?
We haven't got
What
that.
was your conclusion for that?
Oh, in this case, in the previous question, right, so they got they got x bar to be 0.587,
Yeah.
which was bigger than 0.585, so I have enough evidence to reject the null hypothesis.
Oh, so you wasn't saying that both of them, you just wrote them?
This is my answer to part A.
Yeah, but I mean 0.587.
Yeah.
Like when you put x bars smaller than 0.575, you're not saying that's...
No, this is me describing the critical region. So that is the description of the critical region.
Okay.
And then, having got that description, we then go on and say, they got 587, which is in the critical region.
Right.
Alarm bells, I reject that. Something fishy is happening there.
Okay.
Is it meant to be 0.001 because it's a 1%?
No, because when it's a 1% test, but it's a two-tailed test, we halve that. So half of 1% is half a percent, which as a decimal is 0.005. It's how did I know it was a two-tailed test? It's because it didn't say the diameter has gone up or gone down.
Yeah.
They just think it's changed. So there's such a subtle bit of wording. I think I'll pause the camera at that point.